In this video, we're going to talk about the laws of logs. First, let's talk about the values that A, B, and C can take on. We talked in the last video about how A has to be positive. Because remember, that on the left means A to the C equals B. Now, if A were negative, like -3, what would it mean for -3 raised to the square root of 31? Or -3 raised to the 0.378? Or -3 raised to the pi? Or -3 raised to the -1.8. You can't raise -3 to say the square root of 31. What would the sign be? Would it be positive or negative? Can't raise -3 to the pi. You can raise 3 to the pi, but not -3 to the pi. So just like A has to be positive here, it has to be positive here. After all, they're the same A. Now, what about B? What can B equal? Well, so let's denote that A is positive. If you raise A to a number, it's going to be positive. You can't raise A to some value and get a negative number. But remember, whatever A to the C is, that's the value of B. If A to the C is 11, then B is 11. B has to be positive. B has to be positive. And C can be in the real numbers. C can be any real number. C can be an element of the real numbers. It can be any number. It can be 2/3. It can be 1/pi. It can be e to the pi. It can be 7 to the 4/5 power. It can be anything. Okay, now that we talked about what A, B, and C can and cannot be, A can't be negative or 0, B can't be negative or 0, C can be anything. A has to be positive, B has to be positive, C can equal anything. Now, so with these rules that I'm going to write down, you have to be careful about whether or not what I'm about to write is always equal. The log of a product can equal log of x plus the log of y. Notice that the base did not change. The base started off as A, and it's maintained that it's A. Now, it is, so x times y must be positive, because that's what B is. B must be positive. But there's two ways for xy to be positive. Either x and y, well, let's write it down that way. Either x and y are both positive, x is greater than 0, y is greater than 0, or they're both negative. Now, if it's this case, that x and y are positive, then this equal sign is valid, because that's positive and that's positive. But if x and y are both negative, then you can't take the log of x. You can't take the log of y, because they're not well defined. The left-hand side is well defined, but the right-hand side will not be well defined. So all I'm saying is that you have to be careful about domain issues. Can log of x times y really equal to log of x plus log of y? Again, if you have log base a of -3 times -4, -3 times -4 is positive. So this here is well defined. And can it equal to log of -3 plus the log of -4? No, because I'm taking the log of a negative number. Or if you prefer, I'm taking the log of a negative number. This would not be equal. But if we let that 12 be 3 times 4, then it is correct to say it's log of 3 plus the log of 4. So sometimes it's valid, sometimes it's not valid. But as long as everything's understood to be positive, it's valid. If you have log base a of x over y, this is log x minus log y. Again, this has to be positive. X over y has to be positive. If it isn't, then it can't equal this because this is nonsense. If x over y is negative, like -11, log base a of -11 is not well defined. It can take log of negative numbers. Okay. Well, once again, if we have a similar situation. Here we have a fraction being positive. That happens, well, when the numerator and denominator are both positive, or when the numerator and the denominator are both negative. If we're in this situation, then log of x is well defined and log of y is well defined, so the equal sign holds. But if x and y are both negative, look, we're taking the log of a negative number. Oh my, we're taking the log of another negative number. This right side is nonsense. But the left side is well defined, because if you divide two negative numbers, you'll get a positive. X over y is positive. So again, you have to be careful when you do these rules. Sometimes they actually don't hold up. This is quite unusual. Usually when we're given a rule, it works. Okay. Log base a of b to the r. This is log base a of b, and the r comes down in front as a multiple. Well, is this always true? Well, if you have log base a of -2 squared, well, that's log base a of 4, because -2 squared is 4. This is well defined. Oh, so let's bring down the 2. And then we get 2 times log base a of -2. That's not well defined. You can't take log of a negative number. Now, just for the record, you can always get around these problems by putting absolute values. That is, the log of x times y, regardless of what the base is. This is the log base a of the absolute value of x plus the log base y of the absolute value of y. Now, if x and y are both positive, okay, remember this has to be positive, so either x and y are both positive or they're both negative. Well, if they're both positive, then the absolute value of x is just x, and the absolute value of y is just y. That is, you don't even need the absolute values. But they can both be negative. Remember, the log base a of -3 times -4, well, that is the same as log base a of 3 plus log base a of 4, because 3 times 4 is 12. That is, I can write this as log of absolute value of the -3 plus the log of the absolute value of the -4, just in case they're negative, and in this case they are, but this is fine. Same thing with number 3, log base a of b to the r. Obviously, if b is negative, raising it to the rth power made it positive. So when you bring down the log, the r, you can put b in the absolute value bars. That will always work in all 3 cases. Okay. So now let us work on some problems using these rules. Actually, there's another rule that we need to talk about. If you have the log base a of b, and you multiply that by log base b of c, this is just log base a of c. It's almost as if those b's cancel. So you get base a of c. Okay. Now, something very interesting. So actually, let us prove this. Let us prove this. We'll call this a fact, and we'll prove it. How about we let this be u, let u equal to log base a of b, and let this be v, and let v equal to log base b of c. Okay, well, this means that a to the u is b, and this means that b to the v is c. But somehow I want to get a and c connected. So what I'm going to do is I'm going to raise both sides of this equation to the v power, because then I'll get a to the uv equals b to the v, which is c. That is, a to the uv is c. That's all I wanted. When I write this using logs, I get log base a of c is equal to uv. But what is u and v? Well, u is log base a of b, log base a of b times v, which is log base b of c, log base b of c. And I proved what I set out to prove, because that's the same as this statement. So we proved it. Okay. So let us look at this from a different viewpoint. Log base a of b times log base b of c, excuse me. This is equal to log base a of c. Now, if I were to divide both sides by log base a of b, log base a of b, so this cancels out, and what we get is what's called the change of base formula. Log base b of c is log base a, where did a come from? Of c over, a again, of b. I like to call this the lower looking number and that the higher looking number. I'm not saying one is smaller than the other. I'm not saying b is less than c. B is lower looking, c is upper looking. Ooh, look, c is on top, b is on the bottom. And out of nowhere, another base came. What this is saying is, if you have log base b of c, you can write log of c over log of b and insert any base you want, like 7. That is, if somebody asks you, what is log base 3, log base 7 of 8? How much is that? And they give you a calculator, but your calculator doesn't have log base 7 on it. It has ln, that means base e, and it has log, which means base 10. So what you can do is, as long as you do log 8, because that's their top number, over log 7, that's the bottom number, you can pick any base you want, but they have to be the same. Say I pick 10. That is, this is log 8 over log 7. And you can compute that on your calculator. But you remember when I had log 8 and log 7, I said you can pick any base you want? Well, I can pick base e. This is ln of 8 divided by ln of 7. Convince yourself. Now, this is one number. There's only one thing that you can raise 7 to, one value that you can raise 7 to get 8. But I'm claiming that we have two answers. These two answers are equal. Log 8 over log 7 is ln of 8 over ln of 7. In fact, log over log is equal to ln over ln. You can put whatever number you want here and there, any two numbers, but you better put the same two numbers here. You can put 3.8 and you can put 11. Log of 3.8 over log 11 is ln of 3.8 divided by ln of 11. Change or base formula. You can now calculate numbers like log base 7 of 8. It's either log of that number divided by log of that number, or it's ln of 8 divided by ln of 7. I mean, it's not only those two, but those are the only two that we can use a calculator on, because most calculators don't have log base 25. But for the record, this here is also equal to log over log 8 and 7. Pick the base of your choice. 25. Log base 7 of 8 is equal to log base 25 of 8 divided by log base 25 of 7. Doesn't matter what base you pick. Of course, again, if you want to use a calculator, you better either take use ln, or use log. Don't use log base 25, but it wouldn't be wrong. So, if somebody asked you to quickly calculate, they give you a calculator, they ask you to please calculate this number real quickly, pick their log base of your choice. I'll use log, which means log 10. 8, log 8 over log 3. The person next to you, they like ln, that is log base e, 8, 3. 8 goes on top, 3 goes on the bottom. Okay. Now, suppose you wanted to evaluate without a calculator log base 9 of 27. Now, 3 to a power can give you 9, and 3 to a different power can give you 27. So you know what? I want to write this as log 27 over log 9, and the base of my choice is going to be 3. Now, I know what this is. 3 to the third power. That 3 to the third power gives you 27. And you know what? 3 to the second power gives us 9. The answer is 3 halves. Now, this only worked because I was able to write both of those numbers as a power of 3. So, if I give you log base 8 of 16, this is asking 8 to what power gives you 16? You're like, I don't know. Well, this is a power of 2, and that's a power of 2. So how about we do log 16 over log 8, but I'm going to use 2 as the base. Ooh, I know this. 2 to the 4th gives me 16. 2 to the 3 gives me 8. The answer is 4/3. That's a sweet way of doing this. Now, let us do the first one again, and just want to show you there are other ways of doing it. I think we actually did this problem. Suppose we set it equal to x. Well, this means that 9 to the x is equal to 27. But here's the base 3 again. So if you know that 9 and 27 both have base 3, well, you could have used the method up here. Take log base 3. Okay, but maybe you didn't see that till now. So 9 is 3 squared. But I have to raise a 9 to the x power. And 27 is 3 cubed. Oh, that's 3 to the 2x equals 3 to the 3. If you raise 3 to different powers, you won't ever have equality. That means that those powers, since we do have equality, those powers have to be equal. Divide both sides by 2, you get x is 3 over 2. Now, we could have done this one in a similar fashion. You have log base 8 of 16 is x. That means 8 to the x is 16. And when you look at this, you say, oh, 8 is a power of 2, and 16 is a power of 2. But again, if you saw that, those are the same two numbers, 8 and 16, that we're now realizing can be expressed as our power of 2. So we could have done it right from the beginning, and actually we did. Okay, we did it right here. Log base 8 of 16 is equal to log base 2 of 16 over log base 2 of 8, 4/3. But if you're not going to see that, well, 8 is 2/3, and what am I doing to 8? Well, whatever it is, I better do it to 2 to the 3. I'm raising it to the x power. And like we said, 16 is also 2 to a power, 2 to the 4th power. So 2 to the 3x is equal to 2 to the 4th. We have equality. We're raising 2 to powers and we're getting equality. Well, these powers have to be equal to one another. Divide by 3, x is 4/3. Exactly what we got before. Now, you may say, well, no, you didn't. You didn't get x equals 4/3. That's true. I'm not going to argue that. But I said that this was x. This equals x, and x in turn equals that. That means that log base a to 16 is 4/3. And that is what we got initially. So there are two ways of doing that type of problem. Without a calculator, mind you. Now, let us just practice expanding logs. Well, let's just say expand. Expand the following. Suppose you were asked to expand log of a, b, c, d. So the factors are a, b, c, and d. A and b are in the top. So it's plus log a plus log b. The c is in the bottom. So it's minus log c. The d factor is in the bottom. Minus log d. What if you had log of a to the r, b to the s, c to the t, over d to the u, e to the v, and f to the w? Expand this. Well, this would be, since this is in the numerator, it'll be positive log of a to the r. But the r can bring it in front. Plus, that's in the top, it'll be log of b to the s. But the s can come in the front. Next factor, log base plus, because it's on the top, plus log c to the t. But the t can come in the bottom. In the front. Since that's in the denominator, it's going to be negative log base d to the u. But the u can come in the front. Times v, e to the v. Since it's in the bottom, it's going to be minus log e to the v. But that v can come in the bottom. The next factor, f, is in the bottom. It'll be minus log f to the w. But that w, the power, can come in front. So this is in the compact form, one log, single log. This is expanded. Okay. So suppose you were asked to calculate log 2 plus log 5. Now, before you go and run to get your calculator, save some time, because that's going to take too long. Because we can write this as log of 2 times 5. But that's 1. Because remember, log means log base 10. Well, 10 to the 1 equals 10. So sometimes combining them make it easy to compute. What if you were asked to calculate log base 2 of 112 minus log base 2, or 7? Well, the first thing I would do is write this as log base 2 of 112 over 7. But it turns out, now 112 divided by 7, let's see what that is. That's 16. And 2 to the 4th is 16. That means that this mess equals this, which equals this, which equals 4. This is why you have to write equal signs. You don't write equal signs, you lose that beginning equation equaling the last equation. Let's try another one. Suppose you have that you're given, what if you're given this? Log base 12 of 9 plus log base 12 of 16. Well, plus. That means it's log, keep the 12, multiply the 9 and the 16. But that's going to give us a very friendly number. It's 144. And you all should know that 12 squared equals 144. Now, if you have log, sorry, that's not log. If you have log A of anything, this is equal to the anything. This is equal to the anything. That is A log A of Y is equal to Y. Call this a theorem or a fact. The proof is trivial. So, proof. A log base A of Y is equal to Y. Okay? I'm going to take log base A of both sides. Well, on their left side, the power comes in front, and I get that log base A Y times log base AA. Log base AA. So, this is true if and only if that's true, if and only if this is true. Well, this is 1. This times 1, so denote that's 1. This times 1 is just this. That is log base A of Y is equal to, log base A of Y. Of course that's true. So basically, you can prove it by just going the other direction. Clearly that's true. And when I went up one line, all I did was multiply by 1. That's all I did. I took log base A of Y, I multiplied it by 1, and it still equals log base A of Y. And then I can bring this up to the top, so I get log base A of A to the log base A of Y is equal to the log base A of Y. And so on the left side, I'm taking log of this, log base A of that. And on the right side, I'm taking log base A of that. But log is a one-to-one function. That is, you can't take log of two different things and get equality. The log of 7, I don't care what the base is not equal to the log same base of 11. That's not true. Log base 7, log of 7 only equals log of 7. So if log of this equals log of that, that means that what I'm taking the log of have to be equal. A log, well, let me write it the other way. A log AY must equal Y. I mean, I'm not saying that this was not a proof. I'm just saying here's another proof. Just go up. Okay? So, we have this statement. You know, the Y was the anything, and that's what we got. So, what would this equal? What if you had 10 to the 2 log 3? Which for the record is 10 to the log base 10 of 3. Well, you can't use that rule yet until you bring the 2 up. 3 squared is 9. These are the same. So we have a to the log base a of 9 of anything. Yeah, that equals 9. Okay, just bring this up and say, oh, well, let's say it here. Oh, those are the same. That's the answer. That's the answer. So, for example, if you had e to the 5 ln of 2, well, this is e to the ln of 2 to the 5th. Now, you can say right away the answer is 2 to the 5th, or if you prefer, you can say 2 to the 5th is 32, and the answer is 32. If you want to see that you have both of those are the same, remember, ln is just shorthand for log base e. So you get back to anything. This completes the video on laws of logarithms.